Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering the 2019 VCCA Physics Question 8. This is going to relate to, if we're talking about the HSC, Module 5, Inquiry Question 2. So 9 marks, we have a 250 gram toy car, or we can just convert it to 0.25 kg of the apparatus shown in figure 8. The car starts from rest, so it has an initial velocity of 0 at A and travels along the track without any air resistance or retarding friction force, so there's no friction. The radius of the car's path on the loop is 0.2, so 0.2. When the car reaches point B, it is traveling at a speed of 3 meters per second. So at this point here, so u here is 0, velocity here is 3. Okay, it says calculate the value of h showing your working. So this is an example of the total energy initial is equal to the total energy, or I should really write it as E, not the sum. Energy total, fine. So this is a relationship of conservation of energy. So we have our mass of our car, okay, mg plus kinetic energy, half mv squared. That's the total energy of this system that we have here. And then we have our, I might just write U just so we don't confuse initial and final. And then mgh1, h2, because that does change. And then v squared. Okay, so we know that this value is 0 because we have 0 initial velocity at that point there. Okay, we know that the mass is 0.25, acceleration due to gravity is 9.8, and the height it starts off with is what we're trying to find. We reach a height of 0.4, as you can see it's up here, 0.4 from here to here. So 0.25, 9.8, 0.4, plus half, 0.25, v square, which is 3 square, and then substitute all those values together. So let me just calculate the values on both sides, and then I'll add on from here. So on the left-hand side, we have 2.45h equals 2. 2.105, so h is equal to 0.105 over 2.45. So let's see what that gives us as an answer. That gives us 0.8591 in total. Now, if we look at this question here, the lowest sig figs that we seem to have is 2. So 2. Okay, so we'll round it off to 2 significant figures. So we'll get 0.86 meters tall. And that's our height up here. Okay. Says calculate the magnitude of the normal reaction force on the car by the track when it is at point B. Show your working. So if we have a look, our car is here. It's coming down like so. Okay, so we have on the car when it is at point B, so there's gravitational force pulling it down. at the same time, because it's at this position here, the normal force is also pushing down. Okay, and so when these two add together, that gives us our centripetal force. Okay, so I'll just write that out a bit more clearly in case people are a bit confused what I meant. So I'm saying our centripetal force, the reason why it's going in circular motion at this point here, is contributed by the gravitational force and the normal force. If the car was down here, then obviously these two vectors would be in the opposite direction. But because they're both, the car's up here, then both in the same direction that we have here. Okay, so that's what we have. Now we can actually write out the equation for the centripetal force. We know what the formula for the centripetal or gravitational force is, and then this is what we're trying to find. You can substitute the values in first. So the mass is 0.25, velocity is 3, radius is 0.2, and then we write the same thing over here. Okay, so the normal force is equal to this value here being subtracted by this value here. So let's see what value gives us. It gives us a value of 8.8 newtons, in this case going down. Okay, let's look at question C. It says, explain why the car does not fall from the track at point B when it is upside down. So if we have the circle here, our loop-the-loop, so to speak, our car is at this point of the loop. Now it is moving in this motion here. We can also see that our loop is a circular loop, so it's undergoing some kind of uniform circular motion. Now there's two forces acting on our car here. We've already talked about it before. There is the weight force. Sometimes you can write it as FW or FG. And you also get the normal force because it's making contact to the circuit here. When they add together, that gives you your net force. And that so happens to also be your centripetal force. So you could say that our net force is Fg plus Fn, also equal to mv squared over r. Okay, so car in uniform circular motion. So that's kind of the idea. Now the question's asking why it doesn't fall down. Well, there's a couple of things you can look into. The car is technically moving at this velocity here, but to make it really clear for yourself is the fact that there is still a normal force on the car. Remember, the normal force can only exist if there is some kind of contact with a surface. So if there is no normal force, so if there's no Fn, then the only force causing this circular motion would be Fg. And so if there's no normal force, that means there's no contact, so the car can potentially fall down. So if we actually don't consider the normal force in this particular calculation, we can actually work out what the minimum velocity this car would need to be traveling at in order to, have that contact at the very top here and not fall down. Okay. What we can also say is another thing is that the centripetal force or the net force, we actually did a calculation overall. It was about 11.25. So I'll just write that number down here. And that was bigger than our gravitational force.
which was 2.45 newtons. So what we can say is, therefore, there is an additional force that contributes to the circular motion. This is the normal force. And the value of the normal force is obviously just the difference between the two. And we calculated that earlier, which was 8.8 newtons. If, for example, we want to know what the minimum velocity would be in order to maintain this circular motion, so minimum velocity required, then we can do Fg is mv squared over r. Like we said, we are equating this equation because we're saying if there is no contact, then there is no normal force. So the only force contributing to centripetal motion would be Fg. So if we use that value that we have up here, if we rearrange the equation as well, it will be V equals to the square root of Fg times R divided by M. So it become 2.45 times 0.2 divided by mass, which is 0.25. So approximately speaking, I'll just put that in my calculator. We need to travel at a speed of 1.4. So by that means, therefore, the speed of our car, which is 3 meters per second, is also bigger than the minimum velocity, which is 1.4 meters per second squared, in order to maintain contact at the very top here. So that's why our car, does not fall down. So I'll just scroll out a little bit. All right, so hence car doesn't fall at point B. And that's how you do that question. If you found that explanation helpful, please give this video a like, subscribe if you haven't done so already, and I'll see you next time.